Hello and a very good morning to all of you. In the previous video lecture, I covered some basic definitions and plus 4 theorems, right? So in this video lecture, I'll be covering the remaining part of the chapter of the circles, right? So let's move on. First of all, we have theorem number 5, right? Which is that the angle subtended by an arc at the center of the circle is double the angle subtended by it at the remaining part of the circle. Please excuse me with my handwriting, right? As you'll be knowing, it is not up to the mark, but I still hope you got the point, right? So first of all, let us make a circle. Now we'll be covering this theorem in 3 subcategories, right? Since I have mentioned an arc, so we'll first be covering minor arc, then a semicircular arc, and then a major arc, right? So let this be part 1, in which I'll be covering what the minor arc. Clear? So again, what is the main point of a circle? It is the center O. Now let me take 2 points on the minor arc, A and B, right? Now here we are talking about this arc. Let me highlight this with red dots. Clear? Now the angle subtended by an arc at the center of the circle, which is this angle AOB, is double the angle subtended by the same arc at the remaining part of the circle. Let this be point C. So what we have to prove, first of all we'll write the given. What is given to us? A circle with center O, radius R, and a minor arc AB, right? Now what we have to prove? We have to prove that angle AOB is equal to twice of angle ACB. Next, do we need any construction? Yes. The next part comes construction. Join O and C and extend OC to M. Clear? Now let me draw the construction with a dotted line. And let this be point M. Clear? Now we write the proof. Now first of all, let me number all the angles which will be important in proving this theorem, and let this be angle 6. Clear? Now first of all we'll be talking about this triangle ACO. So I write in triangle ACO. Clear? What I write? Angle 1 is equal to angle 2. Why? Because angle opposite to equal sides are equal. Here OA and OC are the radii of the circle. So angle opposite to both the sides will be equal. Clear? I write because OA is equal to OC is equal to radii. The next point, what we come to know, that angle 3 is equal to angle 1 plus angle 2, right? Why? I write here exterior angle property. In the chapter of triangles, you might be knowing that the exterior angle of a triangle is equal to sum of interior opposite angles. Clear? Now since angle 1 is equal to angle 2 and we need angle 2 to prove our theorem, we substitute the value of angle 1 in terms of angle 2. So here we come to know that angle 3 is actually equal to twice of angle 2. Clear? Let me highlight this part and number this as number 1. I hope this much is clear to you, right? Moving on, now I write in triangle OCB. Now no need to write the same stuff again. So I write similarly. What I'll write similarly. Now what will happen, that angle 4 is equal to twice of angle 5. Again, let me highlight this point as number 2. Right? Now simply add up number 1 and number 2. Right? What we will get angle 4 plus angle 3 is equal to twice. I take 2 common because 2 is coming here and here. So I take 2 common out. I write angle 2 plus angle 5. Clear? Now it is almost proved. Angle 3 plus angle 4, that is angle AOB. 2 times angle 2 plus angle 5. Angle 2 plus angle 5 gives us angle ACB. And now we have proved our first part of the theorem, right? I hope it is clear to all of you. So I write hence proved. Moving on, in part 2 of this theorem, we'll be talking about what the semicircular arc. So everything will remain the same, only a diagram will be changed. So in part 2, we'll be talking about the semicircular arc. Right? Now how we'll change the diagram, please note. For the sake of convenience, I'll be taking all points as same. Again, we draw a circle with center O. Now we take the arc as semicircular. Let this be point A, this be B. So I join A and B. Right? Now the angle subtended over here will be twice the angle subtended by an arc at the remaining part of the circle. I again number this as point AOB, right? Sorry, angle AOB, and this as point C. Again, our construction will be same. We'll be joining O and C and extend it up to point M, right? Again, I'll number this angle 1, angle 2, angle 3, angle 4, 5, and angle 6, right? Again, you will see OA, OC is the radii, so angle 1 is equal to angle 2, right? Angle 3 is equal to, sum of angle 1 plus angle 2, exterior angle property. Similarly, in this triangle OCB, and again we will add up, right? We'll get the same result. Now this is our semicircular arc. I hope it is clear to all of you. Now moving on to the third part. What is the third part? We are left with now only one arc, that is known as the major arc. Again, let me use blue pen for this. Major arc. Again, we'll be only changing our diagram to make you understand. Again, I draw a circle with center O, and this time I take the major arc AB. Let this be A and this be B. So the angle subtended by an arc at the center of the circle will be double the angle subtended by it at the remaining part of the circle. Again, let this point be C. Construction will be again same. We'll be joining O and C and extend it up to point M. Again, we'll be taking our same thing again, angle 1, angle 2, angle 3, angle 4, angle 5 and angle 6. Everything will remain the same and we'll get the same result, right? Please pause the video if you don't understand it. Relate to the diagram, everything I have written, right? I hope it will be clear to you, right? Moving on. Now we come to our theorem 6 of the chapter. Now we'll be talking about the properties of a quadrilateral in a circle. Right? What is a cyclic quadrilateral? What are the properties of it? And how do we use it further? Yes. So, sorry, theorem number 6. Now we'll be talking about one thing which I told you. What is a cyclic quadrilateral? Right? So if I simply draw any quadrilateral, right, I am not concerned whether it is a trapezium, rhombus, square, rectangle. It can be anything as long as it is a four-sided figure, right? And I draw a circle, right, which touches or encompasses all the points, all the vertices of that quadrilateral. Then this quadrilateral will be known as what? Cyclic quadrilateral, right? So in simpler terms, if we draw a quadrilateral inside a circle, right, in such a way that all the vertices of that quadrilateral touch the boundary or the circumference of the circle, then that quadrilateral is called as a cyclic quadrilateral, right? I hope it is clear to you. Moving on, what does our theorem number 6 says? That we have to prove the sum of opposite angles of a cyclic quadrilateral CQ, I am abbreviating this, is 180 degree, right? So again I make a circle, right, with center O, and I make a cyclic quadrilateral inside it, something like this, right? And I join the points. O will come somewhere here, so I'll join like this and this. This is our point O. Let me number all the vertices or name all the vertices A, B, C and D. Clear? So first of all we'll write what is given to us. Then we'll write what is the need of construction. Then we'll write to prove, and then we'll finally come to proof. Now what we have to do in the circle, please note one thing, that BD is not the diagonal of quadrilateral, right? BO is a different line segment, sorry, and OD is a different line segment. Please note again that BD is not the diagonal of the quadrilateral. Clear? So what is given to us? A circle with center O and radius R. A cyclic quadrilateral A, B, C, D. Construction? Yes. Join OB and OD. Let me again highlight this point. BD is not equal to diagonal. Clear? What we have to prove? We have to prove the sum of opposite angles is 180 degree, which means angle A plus angle C is equal to 180 degree is equal to angle B plus angle D. Now we come to proof. Now let me consider this arc BD, right? So by a previous theorem number 5, sorry, what will be I doing? I will be writing that angle BOD, right, is equal to twice of angle DAB, right? Theorem number 5, that the angle subtended by an arc at the center of the circle is double the angle subtended by it at the remaining part of the circle. Clear? Now again I write the same thing but with this angle, right? Now I write reflex angle. Please note that my naming has changed, right? Reflex angle, sorry, BOD is equal to twice of angle BCD. right? Angle BCD, again by theorem number 5. In examination, you have to write complete statement of theorem number 5. Please note this, right? Now what we have to do, we have to simply add them. Now we write angle BOD plus reflex angle BOD, right? We take 2 common and we write angle DAB plus angle BCD. BOD plus reflex angle BOD, which means complete angle BOD, will give us how much? 360 degree, right? Angle DAB, this angle can be written simply as angle A, that is the vertex which is coming in the center, twice of angle A, right? And here instead of BCD we can write simply angle C. Now this 2 will get cancelled, this will come out to be 180 degree. So we have proved what, that angle A plus angle C is equal to 180 degree, right? As simple as this. Now we can write what? Similarly, we can prove that angle B plus angle D will also be equal to 180 degree. Hence proved, right?